Hello everyone and welcome back to Diksha Karnataka YouTube channel, and in the second PU midterm series today I am discussing the chapters Magnetism and Matter as well as Electromagnetic Induction. The quick revision of the chapters are already completed. Now it's time for me to discuss the most expected questions from these two chapters. Now one good thing about these two chapters is that there is no 5 marker derivations or 5 marker numerical questions that might come from this chapter. No, that will not happen. And from the first chapter Magnetism and Matter there is no numerical questions as well. So this is a very easy simple chapter. You can score well from this chapter. And Electromagnetic Induction, maybe there a very small 2 marker numerical might come. We will be discussing everything in this series, and if you watch this video, definitely all of your midterm related questions will be definitely covered. Now without much delay I want to start the first chapter Magnetism and Matter, and before I start I request you to subscribe to our channel if you have not yet, and obviously join the WhatsApp group. The link of the WhatsApp group is given in the description of the video. PDF link of this lecture and all the lectures will be shared in our WhatsApp channel exclusively, so don't forget to join there as well. Also share this video with your friends so that they can also learn along with you. Now let's look into the number of questions that I am going to discuss from this chapter. So I am going to discuss 15 MCQ questions. We are going to discuss 5 fill in the blanks and obviously 5 2-3 marker questions from this chapter. This is a small chapter, as I mentioned. Not so many questions are coming, and one good thing about this, everything, all type of questions will be covered in this single video for both the chapters. Now let's start with the first question. When a bar magnet is suspended freely, it points in the directions of east west, northeast southeast, north south, northwest southwest. So we know that when we suspend a bar magnet freely, it point towards the north and south. So option B is the correct answer. I think some options are jumbled. This is the correct answer. The number are jumbled. Next question. The ferromagnetic material among the following is, so you have to identify which of the following is a ferromagnetic material: copper, nickel, lead, calcium. Now only nickel is a ferromagnetic material, copper is a diamagnetic material, lead I am not sure, and calcium is a diamagnetic substance again. Now let's move on to the next question. The physical quantities related to magnetism are listed in the column 1 and the dimensions are listed in the column 2. Identify the correct match. So you have to match the following type of question. So magnetic field, magnetic permeability, magnetic moment. Now this question I think I discussed in one of the previous chapter. Now magnetic moment is very easy to remember. Magnetic moment is very easy to remember. It is matching with this one, right? L square A, ampere meter square is the unit of magnetic moment, area into current. So that's why this is the dimension of magnetic moment. So 3 is matching with B. Now as I said, in case if you have any other doubt, first check the matching that you have done, that is 3 with B, if it is on unique or not. So if it is unique, then your problem is almost sorted. So if you see that 3C, 3B, 3C, 3A. So only 3B is there only once. That means 3B is unique. So definitely this one is the correct answer for this given question. Now statement 1, statement based question. The net magnetic flux through any closed surface is 0. Yes, net magnetic flux through any closed surface is 0 because magnetic field lines form closed loops. The number of magnetic field lines leaving a surface is balanced by number of field lines entering it. Yes, because magnetic field lines are closed loops, so whatever is exiting, same number has to enter. So that's why the net magnetic flux through a closed surface will always be 0. So both statements are true and it is the correct explanation as well. So option A is correct. Next question. The SI unit of magnetic flux is, so magnetic flux is, what is the magnetic flux? Now even though it is somewhat related to the next chapter, you have to understand this. So it is BA cos theta. Now B is Tesla, the unit for B is Tesla, unit for A is area. So Tesla meter square is the unit of magnetic flux. Together there is a short form for this which is called Weber as well. So Weber is the short form of Tesla meter square. So it is Tesla meter square or Weber. So correct answer is Weber. Okay, not Weber per meter, not Weber per meter square, it is Weber or Tesla meter square. Next is universal property among all substance is diamagnetism. Diamagnetism is the universal property. I have discussed it in my theory revision. If you have not watched it, you can go and check that out. Magnetization of a sample is magnetic moment per unit volume. So magnetic moment per unit volume, option C is correct for this particular question. The net magnetic flux through any closed surface is 0. It is in accordance with so net magnetic flux through any closed surface is 0. It is basically Gauss's law of magnetism. So option A is correct. Next, in a permanent magnet at room temperature, domains are partially aligned, domains are all perfectly aligned, magnetic moment of each molecule is 0, the individual molecules have non-zero magnetic moment which are all perfectly aligned. So this is basically talking about domains only, right? So in a permanent magnet domains do not align perfectly, they do align but not perfectly, they align partially. Okay, remember that the in case of permanent magnet or in case of weak magnet, the domains always align partially. If it is not magnetic, then the domains are randomly arranged, they do not align anyway. Okay, so that is the basic thing that you have to remember. Domains are always partially aligned. Needles N1, N2 and N3 are made of ferromagnetic, a paramagnetic and a diamagnetic substance respectively. A magnet when brought close to them will. So if you have three needles, N1, N2 and N3. Okay. Now you have to remember the order, very important, that first one is ferromagnetic, so this is a ferromagnetic, this one is paramagnetic and this is a diamagnetic. Okay, this is the order: ferromagnetic, paramagnetic and diamagnetic. Now if you brought a magnet, okay, if you brought a magnet will have north-south pole, so it will be strongly attracted by this, it will be weakly attracted by this, and it will be weakly repelled by this. Okay, so N1 attract strongly, N2 weakly and repel N3 weakly, so option B is correct. So easy question. Next, the susceptibility of a ferromagnetic substance is greater than, very greater than 1, so it is always very greater than 1. The table that I showed you, you have to remember that table. Now, which of the following properties is false for a bar magnet? Bar magnet given, okay, it does not produce magnetic field. No magnetic field is produced by bar magnet. Its poles cannot be separated. Yes, poles cannot be separated. This is also true. Okay, so this is a true statement, this is a false statement. Okay, so false statement is obviously option A is the correct answer. Let's check the other options. It points north-south direction when suspended. Yes, this is correct statement. It like poles repel and unlike poles attract. This is also a correct statement. So false statement is it does not produce magnetic field. So this is an incorrect statement. Now next question. A susceptibility of a certain magnetic material is 400. What is the class of the magnetic material? So if it is very greater than 1, so 400 can be considered very greater than 1. So definitely it's a ferromagnetic substance. Next, the magnetic field lines inside a bar magnet are from, so magnetic field lines inside a bar magnet. So if you remember for a bar magnet, outside the magnet it goes from north to south and inside it goes from south to north. So they go from south to north. Next, when a bar magnet of a dipole moment M is placed in a uniform magnetic field B, then the torque acting on it, the question is missing, the torque acting on it is M cross B. It is M cross B which is the torque acting on the magnetic needle. Now let's look into the fill in the blanks. The magnetic susceptibility of a paramagnetic substance is inversely proportional to its dash diamagnetic, 0, temperature, magnetization, paramagnetic, ferromagnetic. So if you see that this option, okay, the magnetic susceptibility of a paramagnetic substance is inversely proportional to its temperature. Okay, it's related to temperature, so diamagnetic it is basically inversely proportional to its absolute temperature. That is more accurate. The magnetic susceptibility is negative for diamagnetic substances. Okay, the net magnetic flux through any closed surface is. So if you in case if you have doubt, as I always mention that what you have to do, you have to check whether the sentence is making any proper sense or not. If it is making sense, that can be a possible answer. If it is not making sense, definitely that will not be an answer. The net magnetic flux through any closed surface is, net magnetic flux through any closed surface is always 0. Okay, so answer is 0. The magnetic moment per unit volume is called the magnetization. So magnetization is the answer for this question. Next is the magnetic susceptibility is slightly positive for paramagnetic substance. So correct answer is paramagnetic in this particular case. Now let's look into the 2-3 marker question. Write any 3 differences between diamagnetic and paramagnetic material. Now as you can see, this is the table. If you write it like this, then definitely you are going to make some impression on the teacher. Teacher will know that you have a basic idea and you are a good student. So whenever you are writing your answer, if you write it little bit elaboratively, then that impresses the teacher. That's how you can communicate with the teacher. Even though the teacher does not know you, they will realize it's a good student's paper. So I have to check it carefully. Right, so this is how you give an impression to the teacher. So first you have to write the property. So magnetic behavior, so diamagnetic substance, they are weakly repelled by magnetic field, they weakly attracted by magnetic field. Now magnetic susceptibility, have a small negative magnetic susceptibility, chi less than 0, have a small positive magnetic susceptibility, chi is greater than 0. Effect in magnetic field, so it induces a magnetic field moment in the opposite direction of the applied field. In case of paramagnetic, induces a magnetic field in the direction of the applied magnetic field. Okay, easy question. Mention any 3 properties of magnetic field lines. Very common question. The magnetic field lines of a magnet form continuous closed loops. The tangent drawn at the field at a given point represents the direction of the net magnetic field at that point, and the magnetic field lines do not intersect, for if they did, the direction of the magnetic field at the point of intersection will not be unique. Okay, at the point of intersection. Okay, that is the very basic 3 properties. Now next question, write 3 differences between diamagnetic, ferromagnetic materials. So diamagnetic and ferromagnetic also important in terms of differences. So here also you can, if you remember the same table, you can answer this question again and again. So these are weakly repelled by magnetic field, these are strongly attracted by magnetic field, have a small negative magnetic susceptibility, have a strong, very high magnetic susceptibility. Now they induces a magnetic field in the opposite direction of the applied field, whereas in ferromagnetic they induces a strong magnetic moment in the direction of applied magnetic field. Okay, define magnetization of a sample. How is it related to magnetic intensity? So magnetization of a sample is the measure of net magnetic moment per unit volume of the material. So it is net magnetic moment divided by volume is the magnetization, and magnetic intensity is related to through this equation. We have discussed it. So M equals to chi H. Here chi is called the magnetic susceptibility. Now chi is a dimensionless quantity, so dimension of M and H both are same. State and explain Gauss's law in magnetism. This is also an important question. Gauss's law of magnetism is the net magnetic flux through any closed surface is always 0. So B dot ds closed integral is 0. Physical significance, magnetic monopole do not exist, that is magnetic field lines always form closed loops. Okay, now next chapter, electromagnetic induction. Here we are going to discuss 15 MCQs, 5 fill in the blanks, 5 2-marker question and 5 3-marker question. As I promised, no 5-marker long question. So we are going to complete these 2 chapters very quickly. So now start with the question. The energy stored in an inductor. Also, if you have not yet subscribed, I request you to subscribe to our channel. Subscription is very, very important for us. Okay, we are trying to reach 100K subscription as soon as possible, so that we can bring some more interesting videos for you. Now, the energy stored in an inductor of inductance L in establishing the current is half Li square. So we have discussed in our theory revision, it is half Li square. The following are the statements related to self-inductance. The self-inductance of a coil depends on its geometry and on the permeability of the medium inside. The self-inductance is a measure of electrical inertia and opposes the change in the current in the coil. So both statements are correct. Okay, both statements are correct. In fact, self-inductance depends on the geometry, how the shape, what is the radius, what is the material inside it. It does depend on that, and obviously self-inductance is called back EMF. So back EMF is like trying to stop the current that is being flowed through the coil. So that is like an inertia. Inertia means that resist the change, right? If you remember in the first PU you have learned that whenever a car is in motion, you fall back because your body will try to stay in that state of rest, right? So that's how the inertia was defined. So it is basically trying to resist the change. So self-inductance can be considered, can be equivalently say electrical inertia, and it is obviously the correct statement. Next, the direction of current induced in the loop ABC as shown in the figure. So here if you see that this is basically a question taken from your question bank, slightly higher order question. So if you see that there is a current which is being passed, and there is a ABC loop is given over here. Okay, now if I is increasing or decreasing, based on that there will be an induced current which will produced in this. Now you have to identify how it is. If it is increasing, what will happen? If it is decreasing, what will happen? So first of all, if you know that the current is being passed in this case in upward direction, so the magnetic field line due to this already existing current will be into the page of the paper. So it will be into the page of the paper through the circle. Okay, so it will be into the page of the paper. Now what will happen if the current is increasing? If the current is increasing, the induced current will be such a way that it will try to decrease this magnetic field. Okay, if current I is increasing, that means the induced current will try to decrease the already existing pre-existing magnetic field. If current is decreasing slowly, suppose initially it was 10 ampere, now it is decreased to 8 ampere. In that case what happen is that the according to Lenz's law, that the current induced in the circular loop will try to decrease, will try to make the already existing magnetic field as it is, so that it will try to increase the magnetic field. Okay, so it is always opposite. You have to remember that if current increases, the current induced current will try to decrease the magnetic field. If current decreases, the induced EMF, induced magnetic field will try to decrease the effect. Okay, so always effect is trying to be decreased. If current decreases, magnetic field has to increase. If current increases, magnetic field has to decrease. Now let's see. So along ABC, if current is increasing, now if current is increasing, it will try to decrease it. So try to decrease means the effect will be in this direction. Okay, for a circle, to find the magnetic field, the induced magnetic field, how to find the direction of induced magnetic field, which is very, very important. So in case of a circle, it will be like this, outward. Okay, so it will be in this direction, right? So A, C, B. So if current is increasing, the induced EMF will be in the direction A, C, B. Okay, now if it is decreasing, current is decreasing, so it will be in particular this direction. Okay, so it will be A, B, C if current is decreasing. So along A, B, C if current is decreasing, so option C is correct for this particular case. You have to understand this question. If you have any doubt, please mention that in the comment below. This question came in the past in KCET exam as well, and from there it is being copied to your question bank. Now next, the polarity of induced EMF in a coil is given by Lenz's law. Okay, it is given by Lenz's law. Which of the following is a consequence of conservation of energy? Again, Lenz's law. Okay, Lenz's law, same question, two forms. Okay, so polarity induced in a coil is given by Lenz's law, and the consequence of conservation of energy is also Lenz's law. Similarly, it might come Lenz's law is the consequence of option, correct answer, conservation of energy. Current in a coil changes from 1.6 ampere to 0.2 ampere in 2 seconds, inducing an EMF of 2.8 volt. The value of self inductance in the coil is, so induced EMF is given by L di by dt. Okay, now you have to find the self inductance, which is L. Now induced EMF is given 2.8 volt. L value we do not know. Now current changes from 1.6 to 0.2. So what is dV by the way? So dV will be the change in current, which is basically 1.4. And what is the time? Time is 2 seconds, right? In 2 seconds. So now put the values, 1.4 divided by 2. So from there L equals to will be 2, 1. So L by 2 equals to 2, or L equals to 4. So 4 Henry is the self-inductance. Unit of self-inductance is Henry. Next question, the SI unit of mutual inductance of pair of coil. SI unit of self-inductance, mutual inductance, every inductance, any type of inductance, it will always be Henry. Okay, so mutual inductance or self-inductance does not matter, the unit is always Henry. Which of the following quantity is measured in Weber per ampere? So magnetic flux, electric flux, self-inductance, electric field. So Weber is basically the unit of magnetic flux. Now Weber per ampere is magnetic flux divided by current, so which is basically self-inductance. So the unit Weber per ampere is also self-inductance. So this is the self-inductance. An AC generator is a device used to convert electrical energy to mechanical energy. Device used to convert mechanical energy to electrical energy. So AC generator converts mechanical energy into electrical energy. So this is the correct answer. The SI unit of mutual inductance is, okay, this is a repeat question, some of the same question coming again and again. The expression for motional EMF is BVL. We will do the derivation, don't worry. Next is the magnetic flux through a surface of area A placed in a uniform magnetic field B is defined as BA cos theta or B dot A. BA cos theta means dot product, so B dot A is the magnetic flux. Now, to induce EMF in a coil, the magnetic flux linked must be increase or decrease, so both B and C. It can be increasing, it can be decreasing, both way you can induce EMF, so both B and C is the correct answer. When a magnet is moved with its north pole towards the closed loop, the nearer end coil acts as north pole, south pole. So magnet is moved with its north pole towards the closed coil. So closed coil is there, north pole is being moved towards the coil. So that means the induced EMF will produce a north pole. So north pole will repel each other. That is the Lenz's law. So that is the there will be a north pole. Next, the magnetic flux linked with the coil wire varies as phi equals to 2t square plus 2t. What is the magnitude of the induced EMF at t equals to 0.5 second? Now options are wrong, don't get me wrong. So phi equals to 2t square plus 2t. So induced EMF will be d phi by dt. So it will be 4t plus 2. Okay, and the time is given here as t is equal to 0.5. So put that value over here, you will get 4 into 0.5 plus 2, which is equals to 2 plus 2, that is 4 volt. So the answer is 4 volts. So induced EMF is 4 volt. Okay, next question. The SI unit of magnetic flux is again Weber. I already told you. Now fill in the blanks. The device which works on the principle of electromagnetic induction is, so device that works on the principle of electromagnetic induction, AC generator is the correct answer. Lenz's law is based on the conservation of energy, so this is the correct answer. Self inductance plays the role of electrical inertia, so this is inertia, only inertia, because inertia is the option. Energy is stored in an inductor in the form of magnetic potential energy. It is called magnetic potential energy. Induced EMF always opposes the change in the magnetic flux, so this is always opposes, that is the Lenz's law. So all the fill in the blanks are done. Now let's move on to the 2-marker question. Give the principle of AC generator. Why is a current induced in an AC generator called alternating current? Mention the expression for induced EMF in it. So principle is basically AC generator converts mechanical energy into electrical energy by changing the flux linked with the coil. The direction of the current produced in an AC generator changes periodically, and therefore the current is called alternating current. Now the expression for induced EMF is given by E is equal to epsilon naught sine omega t. Okay, so this is the expression for induced EMF in a AC generator. Now if you see that with time sine omega t is changing plus and minus, that's why it is called alternating current. Alternating current means it is generating current which is varying its polarity with every passing second. So that's why it is called alternating current. State Faraday's law and Lenz's law of electromagnetic induction. Faraday's law, the time rate of change of magnetic flux through a circuit induces EMF in it. Okay, the polarity of the induced EMF is such that it tends to produce a current which opposes the change in the magnetic flux produced in it. So expression is epsilon equals to minus n d phi by dt. Okay, so you can write this out, it will be very good. Next, mention any two factors on which the self-inductance depends. The equation of self-inductance, you can remember this equation, so that will be helpful for you to answer this question. Self-inductance is directly proportional to the square of the number of turns per unit length, so it is proportional to n square. Okay, self-inductance is directly proportional to the cross-sectional area A of the solenoid. Self-inductance is directly proportional to the length of the coil. Okay, so everything is mentioned over here. Now next, a boy pedals a stationary bicycle. The pedals of the bicycles are attached to a coil of 100 turns, each turn of area 0.2 meter square. The coil rotates 6 rotations per second, and it is placed in a uniform magnetic field of 0.01 Tesla perpendicular to the axis of rotation of the coil. Calculate the maximum value of EMF generated in the coil. So what is given? 100 turns is given, area is given. Okay, coil rotates 6 rotations per second. Okay, and is placed in a uniform magnetic field of 0.01 Tesla. So first of all, we have to find the flux associated with it. So what is flux? Flux is B into A and number of turns. Okay, this is the B into A is the magnetic flux linked with one coil. If there are n number of coil, then there will be multiplied by n. Now cos theta is 0 over here. Okay, coil and magnetic field, they are in the same direction, so theta is 0. Theta 0 means BA cos theta, so BA is only required over here. B is 0.01 Tesla, area is 0.2 and number of turns is 100. So from there you get it is 0.2. Okay, so flux linked with this is 0.2. Now it says that it rotates at 6 rotations per second. So it rotates 6 rotations per second. So in one rotation, how much time it takes? Each rotation, the flux linked is 0.2 Weber. Okay, flux linked is 0.2 Weber. So 6 rotations per second. In 1 second it rotates 6 times. Okay, so total flux change or induced EMF, you can write it as d phi by dt. Okay, even though you are dividing by time, what you have to do, you have to multiply by the number of rotations per second. Okay, so if you multiply with the number of rotations per second, you get the total induced EMF, which is equals to 1.2 volt. Easy question. Now there is a one small correction over here. Each rotation actually also associated with 2 pi angle. So you have to multiply that 2 pi over here. Okay, 2 pi over here and 2 pi over here as well. One rotation means 2 pi angle, so that angle you have to multiply and then you will get, it will be 7.54 volt. Okay, so 7.54 is the correct answer. Now next, an aircraft with wingspan of 40 meter flies with the speed of 300 meter per second in eastward direction at a constant altitude in the northern hemisphere, where the vertical component of the Earth's magnetic field is 1.75 into 10 to the power of minus 5 Tesla. Calculate the EMF developed in between the tips of the wings. So EMF developed is given by BVL. This is the simple formula. So the magnetic field is the component, vertical component, which is 1.75 into 10 to the power of minus 5. Velocity is 300 meter per second and the wingspan is 40 meter. So wingspan is the 40 meter. So multiply everything, whatever value you will get, that will be the answer. So let me check 26 into 3 into 4 into 1.75 is 36. Okay, 36 into 10 to the power of minus 1. So that will be 3.6 volt. So the induced EMF is 3.6 volt. I think there is some mistake over here. It will be 3.6 volt, right? Next, derive the expression for motional EMF induced in a straight conductor moving perpendicular to the uniform magnetic field. Now in this particular case we are going to derive the expression of BVL. So for that, what we have to do, we have a frame over here and a rail which is moving along this track. You can consider this to be a track line. Okay, the track line is closed and this is like a train which is moving with a velocity v. Okay, at this instant, at this particular instant, the diagram is necessary, compulsory for this derivation, by the way, if you are thinking. So at this instant, what is the area? First of all, we have to find the area. So area is given by x into the length. So the length is L. Okay, so at this particular instant, the area is given by L into x. Okay, so what is the flux associated with this area? So flux is given by the magnetic field into area into cos theta. Cos theta is 0, cos theta is 1 over here, so only BA is sufficient, right? So put that value, so B into L into x. So this is the flux associated with. What is the induced EMF? Formula for induced EMF is always d phi by dt. So just differentiate it. So B is constant, L is constant, only x is changing, so dx by dt. Okay, x is changing. If this rail moves over here, the value of x will be changing, right? So the x is only factor that is changing, so we can say that dx by dt. Now dx by dt, if you go back to your first PU, dx by dt is nothing but if the distance is changing with time, that gives the velocity. So from here we can write BLV, or the induced EMF can be written as BVL. Very simple, easy derivation, not super difficult, right? Only one differentiation. If you do the differentiation, everything becomes easy. Okay, so this is the induced EMF. Next, describe an experiment to demonstrate the phenomena of electromagnetic induction using a bar magnet and a coil. So here you have to write down this is a descriptive question. So this is a coil and a magnet which is moving towards this coil, and how the EMF is getting induced. So when a magnet approaches the coil, the galvanometer needle deflects, indicating a current is induced. When the magnet is pulled away, the needle deflects in the opposite direction, showing that the current reverses. No current is induced when the magnet stationary related to the coil. The conclusion of this experiment demonstrate the electromagnetic induction in a current is induced in the coil when the magnetic flux through the coil changes. This confirms the Faraday's law of induction, and the direction of the current follows the Lenz's law, opposing to the change in the magnetic flux. A horizontal straight wire 10 meter long is falling with a speed of 5 meter per second at right angles to the magnetic field of 0.3 into 10 to the power of minus 4 Tesla. Find the instantaneous value of the EMF induced in the wire. So 10 meter wire, okay, it is falling, okay, at a speed of 5 meter per second. Okay, magnetic field is given, B is given, which is 0.3 into 10 to the power of minus 4 Tesla. Okay, so what is the induced EMF? Induced EMF is BVL. So B is 0.3 into 10 to the power of minus 4, V is 5 meter per second, and L is 10. So from here we get 1.5 into 10 to the power of minus 4. No, minus 3. 5 into 0.3 is 1.5. So 1.5 into 10 to the power of minus 3. 10 to the power of minus 4 and 10. So 10 means 10 to the power of 1. So 10 to the power of minus 3. So this much volt or 1.5 millivolt. Okay, 1.5 millivolt. You can leave the answer as 1.5 into 10 to the power of minus 3, or you can keep it as 15 into 10 to the power of minus 4. Both are fine, or you can write it as 1.5 millivolt. Everything is correct and fine. Lenz's law is the consequence of law of conservation of energy. Explain. This is a very interesting question and might come, so you have to write this description properly, read it once. When a changing magnetic field induces a current in a conductor, the current creates its own magnetic field. According to the Lenz's law, this new magnetic field opposes the change that causes it. If the induced current did not oppose the change, it would create a runaway situation where the system gains energy without any input, violating the law of conservation of energy. For example, if you move a magnet towards the coil, the induced current generates a magnetic field that repels the magnet. Okay, you must do not do extra work to push the magnet closer, and this work is converted into electrical energy. Thus no energy is lost or created. This is the transformation from mechanical energy to electrical energy. Okay, so basically what you are doing, you are converting a mechanical energy into electrical energy. That's why it cannot have a runaway effect, right? That's why Lenz's law is always valid. A solenoid of inductance 2 Henry carries a current of 1 ampere. What is the magnetic energy stored in the solenoid? Magnetic energy stored in a solenoid is half Li square. So it is half L is 2, current is 1 ampere. Okay, so it will be cancelled. So 1 joule is the magnetic energy. 1 joule unit is very, very important in this case. 1 joule is the unit of energy. So 1 joule is the magnetic energy stored in the solenoid. Now this is the end of this lecture. Now if you have not yet subscribed to our channel, definitely I will request you to subscribe to our channel. I'll be back with another chapter very soon, that is alternating current. Alternating current we are going to do next. Before that, I am saying goodbye and all the best.